Have you built an awesome GNSS simulation with jammers, spoofers, and multiple constellations, but you're worried you might be pushing the simulator to its limits? Or maybe you want to know if you can lower the latency to 20, 10, or even 5 milliseconds. These are great reasons to use the real-time performance graph. So let's dive in and take a look at this one-of-a-kind feature in Skydel. The graph is located on the Performance tab in the bottom pane of Skydel. A summary of the performance data for the last minute is located on the left-hand side. A more detailed graph of the previous second is on the right-hand side. To properly understand this graph, we need to know how the engine works under the hood. The engine processes the simulation in 1 millisecond chunks. Each chunk passes through 3 workers: the constellation worker, the modulation worker, and the streamer worker. The passing of chunks through these workers is known as the pipeline and is a major factor in determining the latency of the system. For any given chunk, the engine knows exactly when that chunk will be transmitted by the radio. Because the transmit time is known during the calculations, the time prior to RF can be determined at every stage of the pipeline. So, when the constellation worker begins working on a chunk, the time prior to that chunk being transmitted is recorded. The same happens when the constellation worker completes the work on that chunk. This process is repeated for the modulation worker and streamer worker. These start and finish times for each worker are displayed on the graph by connecting the start time to the finish time with a solid line. These colored lines indicate when a worker was busy: blue for the constellation worker, red for the modulation worker, and green for the streamer worker. One chunk is 1 millisecond, so it takes 1,000 chunks to complete the graph. Something important to note here: if the simulator fails to perform the calculations fast enough, an underrun occurs. This means that the radio didn't receive data in time to transmit. When this happens, the simulation will stop and indicate an error. What's cool is, the real-time performance graph shows you exactly why and when the underrun occurred. It's when any of the worker lines hit the x-axis. As the simulation continues, data from the previous second graph is condensed and displayed on the previous minute graph. Each data point on the previous minute graph corresponds to 1 second of simulation. The colors mean the same as before, but now the heights represent the earliest start and the latest finish of the 1,000 chunks during that 1 second. This allows you to quickly see the overall performance of the system. The main point is this: lines staying near the top of the graph indicate the system is running smoothly, with low risk. Lines dipping near the x-axis indicate instability, with higher risk of underrun. Let's see how the graph looks when the system is not performing well. To achieve this, I'm going to lower the clock speed of the processor on the system. As you can see, the streamer is not performing well. It oscillates between falling behind and catching up. If it ever hits 0 milliseconds, it means that the streamer is currently performing calculations on data that should have already been sent to the radio. This results in an underrun, which stops the simulation. The real-time performance graph clearly shows that the simulator is not running well and can be used to diagnose the cause of underruns. Now let me change the processor clock speed back to normal. You can see the streamer performance improves immediately. Seeing this improvement in the real-time performance graph helps build our confidence that the system is running well. By using the graph, we can determine how much time the engine needs to generate the RF data. For this configuration, let's run the simulation with the latency set to 5 milliseconds. This guarantees the simulator engine will have at least 5 milliseconds to perform the necessary calculations. You can see we are pushing the system to the limits, but as long as the constellation, modulator, and streamer stay away from that 0 line, the system is stable and will continue to simulate. Now let's try a hardware in the loop simulation, or HIL for short. The purple dots on the graph indicate what time the HIL packets were received. The higher up on the graph, the earlier they were received relative to the corresponding RF event. In this example, we are sending the HIL packets too early, and we are inducing a latency in the system. It would be better if the HIL packets were arriving closer to when they were needed. Let's adjust the hill sender so those packets arrive exactly when they need to. Okay, you can see those purple hill dots are now arriving 5 milliseconds before the RF event. This means that from the time the simulator receives the hill packet to the time the RF is output on the radio is only 5 milliseconds. Our hill sender still isn't perfect. Do you see where the purple dots drop below the engine latency? That means the hill packet was received too late. The constellation worker had to extrapolate the previous hill data to begin performing calculations. Ideally, the hill sender would never send a packet this late. The graph helps us diagnose these types of problems, allowing us to improve the interactions between the hill sender and the simulator. The real-time performance graph will give you confidence that your simulations are running reliably and with low latency.